Hey, quantitative reasoning, we're going to do scatterplots and correlation today. So, not every single piece of data makes a perfect line. Sometimes they're close, but they don't make a perfect line. So, an example of a positive correlation. So, if you had a coordinate plane, just the quadrant 1 right there. Let's lighten that up a little bit. So, positive correlation, you collect some data, and maybe it looks like this. So, when you collect data, not everything is perfect. But if you were to draw a line through this data, you would see that, you know what? Those points would be fairly close to a line if I chose to draw one. On positive correlation, as the x goes up, the y also goes up. It is like positive slope. For negative correlation, it might look something like this. In this case, as your x value goes up, your y value is going down. So here, when x is little, y is really big. As you move over here, as x is really big, y is really small. This is like negative slope. And then finally, we would have no correlation. Maybe it looks something like that, where you cannot find a pattern. You just kind of have some data that's all over the place. Here I would say no relationship between x and y. All right, so in addition to positive and negative correlation, we have something called, we could judge how strong or how weak the correlation is. So the strength or weakness of the correlation is determined by how clustered or widespread the values are to the straight line. So I would say that something has a strong correlation if the majority of points are close to the line. So if you went ahead and you looked at the graph right below that, I would absolutely call that a strong correlation. So we have our data points here. We have this line that goes through it. The line that we keep referring to is called the line of best fit. A weak correlation is points are not close to the line. So here we have the equation of the line of best fit. So this equation right here, y equals 1.6176x minus 2864.6. So that is the equation of the line of best fit right there. This R value right here, so anyone that goes on to take a statistics class, you will probably learn much more about this. This R value is what we call the correlation coefficient. Correlation coefficient. The correlation coefficient is a number that tells the strength of the correlation. I was watching a really good video. I found this Ivy Tech video, and he was doing a fantastic job, and he relates it to grades. He's like, okay, so you know you want an A. So if you have like a 90 or better, so this is an A. So you want an A, which would be a .90 or better. So if you were going to look at any kind of study that was out there, you would be able to find the correlation coefficient. Any decent study, he said, would have a correlation coefficient of 90 or better. If you do a study and you have a correlation coefficient of 70, then there are some weaknesses that are happening there. So as you look at this data here, you have to decide and be able to look at it visually and say, is this representing a positive, a negative, or no correlation between the variables? So once again, that's why I relate it to slope. Right here, are you looking at positive slope, negative slope, or I cannot judge this? I am definitely looking at positive slope, so I would say I have a positive correlation here. All right, so we have gathered some data over time. So if you can't read that, and you probably can't read mine now anyway, that says 1970. So right here, this is not actually the y-axis. This is probably the first year that they started gathering data. So in 1970, and then they gathered some more information in 75, 80, 85, 90, 95, 2000, 05, and 2010. This y-axis right here, in case you can't read that, that is at 300. There's 320, 340, 360, and 380. Those are what those values are on the axes. What value does the model predict the concentration of carbon dioxide in the year 2000? When it says model, that is saying, hey, I need you to use the equation. So you don't want to, you can look at the graph, but that really says, hey, plug this value into the equation. But we have a nice graph here. So if I were going to double check myself, I would probably look at the graph first of all. So in the year 2000, if you follow it up, and then you follow it to the left, you would see that that value would be between 360 and 380. And it seems to be pretty well in the middle, but from the graph, I know that I would expect an answer between 360 and 380. So this equals 2000. That is going to be the x that I plug in. So the equation that's up there, I'm going to use all the decimal places it gave me. 1.6176. So that is my x. So I'm going to go ahead and plug 2,000 in right now because I know I'm going to run out of room. Minus 2864.6. So if you used your calculator and you ran those numbers, you would get an answer of 370.6. So the model, aka the equation, says that the concentration should be 370 in the year 2000, and that completely coincides with my graph. So I think I did that correctly. So the graphs and the equation, they work really well when we want to, it's called interpolate the data. So if you wanted to find data at any point between the year 1970 and the year 2010, this does a fantastic job of that. Number 3 says, okay, but what is it in the year 2024? Well, 2024 is pretty much off the graph. So, while we would like to think that this line would continue on forever and ever, it is a little bit dangerous, especially the more years that you go out, to know that this equation is going to hold and still be true 14 years later. But that's what we're going to do. So, I'm going to plug 2024 in for x. So I ran those numbers and my calculation said that it was 409.4224. All right, so some things go up over time. Apparently, the carbon dioxide in the air has been going up. However, some things go down over time. We go to the next page. We have a scatter plot. And it says, hey, this is an example of negative correlation. It tells you in the problem. So as your x value goes up, your y values are going down. So over here it told me what the equation was, and it was a little hard to read, so I retyped it. It's right there for you all. Please note that that is definitely a negative number in front of your x, and that's got to be because a negative correlation means that you have negative slope happening. So you got to have that negative right there. I think sometimes it's called r squared, sometimes it's r. It's been a while since I've done stats. But I do know that this is trying to describe your correlation coefficient, and it's at 0.8941. So that is a solid B+ on the grading scale. So it looks like this correlation is pretty good. What value does the model predict when x is 45? All right, so here's where 45 is. So when I go up and I go over, my graph says I should be at about 170. But it says use the model to predict it. So I'm going to plug 45 in for x right there, and I'm going to see what the model gives me. And you run those numbers, and you get 175.295. All right, so we interpolated this data, so that is pretty accurate. However, it wants you to predict the value when x equals 150. So that is way off the chart. So we can't be 100% sure that this is going to give us an accurate answer, but we're going to follow the instructions. So we're going to run those numbers in our calculator. And I get 46.88. You're doing good. All right, so we've been talking about the line of best fit. I haven't really defined it, but I'm telling you the line of best fit is the solid line that is in the middle of all of your data points. So we would like, when we draw the line of best fit, we would like to find the equation of a line that is kind of the average of all these. So ideally you should probably have equal amount of points above and below the line. So this is a line drawn on a scatter plot. That best represents the data. Should be in the middle of the majority of the points. So the prediction equation is the equation of the line of best fit. It's probably been since Algebra 1 since you've had to do this. So in Algebra 1, you guys did scatterplots. And so it's probably been a while since you've had to write the equation of the line. So here's what you do. Using some upper and lower points, you're going to find the slope. So we have the line on here. So this solid line, that's what we're trying to do right now. We're trying to write the equation of this line. So the first thing that you really need to do is you've got to find the slope of the line. All right, so I look in the background and I look for any 2 points on the line that are crossing at some grid points. And so what I see is I know that I have this point right here at 33,160. And I see that I also have this point right here on the line at 34,150. So you can find slope using rise over run. So I had to count down and then over. But you got to be careful here because when you count down, you actually counted down a total of 10 units. And then when you went over, I only went from 33 to 34 in the grand scheme of things. So your slope here, I went down 10 and right 1. So I know that my slope is negative 10 on that one. You slope, pick 2 points. I did that. Substitute the slope of the point. Use the slope and pick one of your 2 points. All right, so we have to do this. This is actually B down here. So if you wanted to jump down to B, that is where it is telling you find the equation of the line of best fit. So for slope, we did the rise over the run, and we got negative 10. There are many, many points on the line. I'm using the one at the top corner. I'm going to use the points 33, 160. Although any point on that line would be fine. But when you choose a point, it has to be on the line. The point that you choose is your x1, y1 coordinate. And from above, I'm rewriting the equation. So I have y minus y1 equals m times x minus x1. That says y minus y1 equals m parenthesis x minus x1. So this is called the point slope form. So the first y stays. In place of y1, that's when you're going to substitute in 160. Your slope is negative 10. This plane x, that always stays, that's x. And then your x1 value is 33. We would like to have all of our final answers in the form y equals mx plus b. So my plan is to distribute to clear parentheses. Negative times negative goes plus 330. I want to solve for y, so I cross that off because I'm running out of room, and I'm basically just adding 160 to both sides. So 330 plus 160 adds up to 490. So this one is your y-intercept. So I will say that on this particular graph, you have to be super careful. This does not have a y-intercept of 160 because that value is not 0. That isn't the y-intercept. That is just the point 33, 160. So this on this problem, since it didn't start at 0 on the x-axis, you had to do this. All right, we have all kinds of info now. Let's see. So what is this graph? Michael swam 2,000 yards on each of 18 days. The scatter plot shows his swim time and the corresponding heart rate. The line of best fit is the average of all of these swim times right here. 5A says, for the swim that took 34 minutes, Michael's actual heart rate was how many beats per minute less than that predicted by the line of best fit. All right, so we care about 34 minutes. All right, so there's the yellow highlight. That is focusing on the 34-minute mark. So if it asks you a question like this, you need to know that the actual is where the dot is. So I have a whole lot of crud going on here, but if you look here and then you go over, do you see what his actual heart rate is? 148, because this seems to be counting in increments of 2. It wants you to compare that to the predicted. So we really just have some vocabulary here that you need to know. So when it says versus the predicted, that's not spelled right. That's the word predicted, by the way. Promise. That means, hey, now you have to go to the line. So at 34, you go to the line and you go over, and you're like, oh, the line said that should have been 150 beats. And so then it just wants you to say something about it, and that is just simply that the actual is 2 beats less per minute than the predicted. All right, last one for today. 5C says, what value does the model predict for the heart rate after swimming 33.5 minutes? All right, so you need to know that the X is the time, and if you look at the label on the X-axis, it says the swimming time is in minutes. So you got to know that X is your time. We just wrote an equation a few minutes ago, so I'm using y equals negative 10x plus 490. That is my model. I'm going to plug 33.5 in for x. I'm going to run those numbers in my calculator. And that should be 155 beats per minute. All right. Check the next video for the rest of the notes.